All right, recording is rolling. It is Tuesday, March 12th. We're a few minutes into class. You guys just saw these two uh, video examples, right? So this is train paradox and also GPS, so global positioning system that you guys probably use in your phone to like navigate around. Wouldn't actually work accurately without like understanding the theory of relativity. While you guys watching that, I gave you guys algebra-based questions for relativity, so I'll go over some of these with you guys today. And then the last couple minutes of class, I'll show you guys a proof for this mass energy equivalence equals MC squared. Okay, so real fast recap from yesterday. I was introducing you guys to this idea of relativity. So I'll start with like what is the speed of light? Here's the first way it was accurately found back in 1849. Then people try to figure out something about those. What's the relative speed of the luminiferous ether, which they unintentionally actually disproved. Right? Also, the fact that it doesn't matter what your frame of reference is, you always perceive the speed of light to be the same. Right? That was weird, but then Einstein correctly interpreted this as being like, oh, well, if you put yourself into motion, time actually dilates. Now, if you're along for the ride, like inside this train, or turns the train to a rocket, maybe that would be a better example. Right? You don't actually notice anything weird in your immediate local surroundings, right? But if you have, say, like Earth Twin and Rocket Twin, you guys remember yesterday played an animation called Twin Paradox, right? The Twin Paradox, right? Then when these twins meet up, right? If Rocket Twin's been flying around near the speed of light for some time, turns back and meets up with Earth Twin, they will disagree about how much time has passed, right? So you can use Pythagorean theorem, show here's this time dilation. So here's Rocket Twin time, Earth Twin time, right? This square root is called the Lorentz factor. Square root of 1 minus b squared on c squared. C is the speed of light. V could be the speed of like a train or a rocket. Okay? So this Lorentz factor, the square root, is always bounded between 0 and 1. What does that mean for the comparison between these differing time values? Well, take rocket twins time, say like he says like 1 year has passed. I've been flying around at relativistic speed for a year, and divide by something between 0 and 1. That's going to blow up the answer bigger than 1 year. Here, I'll prove it to you guys. Right, so square root of whatever is bounded between 0 and 1. You plug in whatever you want for v. This is between 0 and 1. Let's take 1 year divided by, let's say it comes out like 0.5. That means it's 2 years for Earth Twin. Earth Twin says 2 years have gone by. Rocket's it's only been a year. Right? Right. So different passages of time, right? Because he accelerated up to that relativistic speed. Right? Now it's not just time to dilate, it's also you get a length contraction. That was what you guys just saw with that train paradox. The train going into the tunnel, right? Is the train shorter than the tunnel, or is the tunnel shorter than the train? Well, it depends on your frame of reference, and then that introduced the idea of simultaneity. Relativity of simultaneity, right? All right. There's also this momentum dilation. We'll look at a example with particles, right? So speed of a particle near the speed of light, right? Its momentum is going to asymptotically approach infinity, right? Which should deviate from what Newton predicted. We're looking at Minkowski space-time diagram. Okay. Mass energy equivalence. This is the energy of nuclear reactions. We'll look at a couple of questions today on this one, right? And I'll show you guys a proof here at the end of class, right? Of like where the full thing where this comes from. Okay. Right, so talking about fission and fusion reactions, right? There's some change in mass for a nuclear reaction, not a conventional chemical reaction. Change in nuclear reaction, there's going to be a change in mass, and that change in mass multiplied by the speed of light squared tells you how much energy you're getting from that reaction. Right now, the bell was ringing about here yesterday, so some classes saw this and some not. So here, I'll do this one a little bit more thoroughly. Right, now let's fast forward to 1916 because everything I've done so far is like 1905. Einstein published special relativity, right? 1916 he incorporates gravitation. Says, well, gravity also slows down time. Right? This is one of his general relativity expressions. Right? Now, and you guys also saw an example application of this, also GPS. Right? So those GPS satellites, right? Your phone is getting signals from at least like 3 or 4 satellites at any time to locate your position on the surface of Earth. Right? But clocks run differently up in those satellites for 2 competing reasons. The fact that satellites go so fast slows down time for those satellites, but the fact that they're in weaker gravity fields speeds up time, which is actually a larger effect. Right? So the satellites have to have atomic clocks that are adjusted to account for these 2 competing effects within relativity to be able to accurately tell you where you are on the face of Earth. Right? So there was this solar. Let me jump to the story. a solar eclipse, which we have one coming up in just a few weeks. Right, solar eclipse. But I'm thinking 1919, there was one. Maybe I should say a total solar eclipse, right? Now, why was this important to as the first experimental evidence for general relativity? So Einstein published this in 1916. People are reading these papers saying, that seems pretty wacky. What gravity slows down time? What evidence do you have of this, right? And Einstein says, well, that would cause, for example, gravitational lensing. Okay? And if you take a picture of, say, like the eclipse during a total solar eclipse, you can see evidence of that. So here's the claim he was making. Say, let's say you have the sun here, right? And if you could, let's throw the Earth on here. Like here's the Earth, right? So we got the sun, the Earth, right? Now, if you're looking towards the vicinity of the sun, maybe say like in the background there could be some stars, right? Maybe like on the outskirts of the sun in the back. So throw some stars here. Well, I'll throw at least one star on the board, right? Right. And if you were able to see it, maybe like be right on the outskirt of the sun, right? So maybe I'll do like a dashed line, be like right there, right? But you guys know during the day you can't see any stars; it's too bright. You definitely can't see any near the vicinity of the sun, right? If you have like special equipment, no, it's just too bright, right? It just drowns out all the light, right? Unless you have a total solar eclipse. Let's throw the moon in here, right? So now the moon, here could be the moon, right? Is completely covering blocking the excess light from the sun, right? Well, now you should be able to see the stars in the vicinity of the sun, right? But they'll look a little bit bent out of place. So this star is sending out rays of light in all different directions. Right, let's follow a different ray of light. What about one that goes kind of this way? But then what's coming around the sun? Now the sun is the largest, has the largest gravity field of anything nearby us. That's why an eclipse is important too. Right, so we need this gravitational lensing from the sun. Right, so the gravity from the sun will actually bend light. Now, there's another prediction that maybe doesn't really align with Newtonian gravity that I taught you guys last semester. Last semester, you guys learned Newtonian gravity is F equals gmm over r squared. So anything that doesn't have mass should not be affected by gravity, is what Newton would have said. Light doesn't have any mass. But Einstein says, no, actually, light follows a straight path through, in this case, curved space-time. He's making the case. So that from the point of view of Earth, what it would look like? Well, it looks like the stars come from there, must have come from back like here, right? So now you can do a comparison. You say, well, during the regular night sky, we know where all the stars are in the night sky. Okay, so we got that map, right? Now during a solar eclipse, we'll take that picture, took some photographs, right? And yeah, in fact, the stars were shifted a little bit. They were gravitationally lensed a little bit. But as much as Einstein had predicted, he made an exact prediction for exactly how much the stars would be shifted in the night sky, and he was exactly correct. Right? And so there you go. That was the first experimental evidence of general relativity. And of course, nowadays we have to even incorporate that into GPS. Okay. Right, so you guys get there? That one? Okay. Sometime coming up soon, I'll play you guys a TED Talk on dark matter and dark energy, which are totally different concepts, but there's a relativity connection there too. So hang tight for that one. That'll be another day. All right. So plan today is to do these questions on this. Pause this video here. Pause. All right, record and resume. We're back here. All right, so everybody got this page, right? So on this side I'm looking at here, there's 12 questions related to relativity. And oh, look, in the equation bank, I gave guys the dilation formulas that we were just reviewing, and also the mass energy equivalence, E equals mc squared. Okay. On the back side of this is Fizeau's cogwheel. He's trying to measure back in 1849 what is the speed of light. So we'll save this one for later this week. I want to fit in later. Okay. But today we're going to focus on these questions. Right. So and the way I want to do this is set up a lot of these with you guys, solve a couple of them with you, and then give you guys some time in class to work independently on them. So we're going to focus on 1 through 6 and number 12. Right. Actually, let me do this a little out of order. Right. Let's go hit the two conceptual questions first. They're at the bottom of the paper. You see number 5 and number 12? Right. Let's knock those out first. Then we'll go do all the calculation ones. So number 5, where does time tick faster due to special relativity? Now, that's the one we focused on mainly yesterday, is the if you put something in motion, say like you're thinking twin paradox. You guys remember Earth twin versus rocket twin, right? Right. So who does time tick faster for? And your answer options are Earth twin or rocket twin. Earth twin or rocket twin, basically. You guys said, right? Right. Now, a couple ways you can figure this out. Right? One way is maybe you just remember the story. there was Earth twin, there was rocket twin. They started off the same age, but rocket twin took off in a rocket flying close to the speed of light. And it comes back in the news with Earth twin. Guys, which twin got really old? Was it Earth twin or rocket twin? Earth twin, right? Which actually does answer that question, right? Rocket twin says, oh, it's only been a year. Earth twin says, it's been 20 years. Right? So yeah, so time's been taken faster for Earth twin and slower for rocket twin, right? Right. So that answers the question. Or maybe what I like to emphasize too is to read the music of these equations. So if you look at the time dilation formula, here's time for Earth twin compared to, and then it says the fraction, time for rocket twin, right? And then divide by this Lorentz factor, 1 minus v squared and c squared, right? Now, no matter what you plug in for v, right, this Lorentz factor square root is always bounded between 0 and 1. So if rocket twin says like a year's gone by, and divide by, pick any number between 0 and 1, say 0.5, say, oh, like 2 years, right? So like more times passed for Earth twin. Therefore, if they're comparing clocks, like if they got telescopes and they're looking at each other, right, like through the window of the rocket, right, Earth's looking at rocket twin's looking back at Earth, looking at clocks ticking, right? Right. They each think their own clock is ticking 1 second per second, but they think the other guy's clock is ticking differently, right? So rocket twin's clock looks like it's going tick, 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 right? And then rocket twin looking back at Earth twin's clock looks like it's going tick, 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 right? So different rate, right? That answers that question. Number 12 is a general relativity question. Where does time tick faster due to general relativity? So now we're thinking about gravitation, right? And I've got surface of Earth or surface of the moon, right? Well, you guys know Earth has more gravity, the moon has less gravity. So how does that affect time? And you saw the answer in this GPS video. I was saying the fact that GPS satellites are further away from Earth than the surface, the gravity field is weaker. Therefore, time ticks faster where there's a weaker gravity field, and they have to adjust for that, right? So where does it tick faster between Earth and the moon? What would you guys say? The moon, because there's less gravity on the moon, right? Again, this is a really subtle effect. This is not something that you would notice with just a human brain, right? You have to have atomic clocks, like special equipment to notice the difference. But yeah, it does make it a difference. All right, now let's go into these algebra based. So, all right, we'll do all the ones on the left and then number 6, and I'm gonna save the other ones for a different day, right? Maybe tomorrow. Right. The first three are these first 3 questions are going to line up with these 3 dilations right here. Right. So number 1, Earth twin stays on Earth, rocket twin takes off in a rocket, flies around close to the speed of light. In the situation when the two meet, how much time has passed in Earth twin's frame of reference? Right. So in this table of values, what did I give you? Right. So from right to left, I gave you the speed of light. I gave you the speed of rocket twin's rocket. Suppose he gets up to that pretty fast and he just like zooms around for a long time. Okay? And then I've got 2 different columns for time. Remember, T naught is rocket twin's time. So I gave you rocket twin's time. Now, like usual for these papers, my numbers are different than your numbers, right? But we all have all the same scenario. So we can use all the same method to solve this. So let's go time dilation. I got, wait, did I actually start that? Here, I've actually got that started right here. So nearly label this number 5. Let's just change this to number 1. It's the same setup, right? All right. So I'll go ahead and solve mine for this one. So Earth twin says how much time has passed, right? So set up a fraction, right? Now my rocket twin has 24 hours. 24 hours. So I'm going to put 24 hours, right? Now your paper probably has said something different. You guys see your T naught? What was your time for your rocket twin? Right? Mine says 24 hours. Right? Then divide by square root, right? Open parenthesis. I'll do 1 minus and set up a fraction. I got the speed of my rocket is 2.1 times 10 to the 8 meters per second. Right? And don't forget to square that. Right? Again, you probably have a different speed for your rocket, but I bet it's 10 to the 8 meters per second because I wanted to give you a relativistic speed so you could see a significant dilation. Right? And then divide by speed of light being squared. That's 3 times 10 to the 8 meters per second, and then square that. Right? So that's all grouped underneath that radical. Right? You guys get that? Right, so calculator time. And I can actually do a little shortcut too. Do you guys see 10 to the 8 and 10 to the 8? Now it's being squared, but you just think it still cancels out the 10 to the 8 bit? All right, so it saved you a little bit of calculator work there. So I plug this in as 24 divided by the square root. The square root and everything from here on out. So just to be safe, I'm going to open up some extra parentheses so I don't close them too early. I do 1 minus, and then open up another parenthesis. I'm just going to go. Let me see if I do. Yeah, let me pause this. All right, back recording. So then, again, cancel out the 10 to 8. So 2.1 squared divided by 3 squared. All right, I'm getting, this is 33.6, and the unit would be hours to match the original unit. Right? And that is an answer choice on my paper, so that's my Earth 1 time. Right? So if you fly around at close to 2/3 the speed of light, then Rocket Twin says 24 hours has gone by, but for the same interval, Earth Twin says, no, it's been a lot longer than that. It's been close to 34 hours. Okay. Okay. Are you guys getting hopefully an answer on your paper? Okay. Hopefully. Yep. All right. Okay. Let's check out number 2. We still got the twin paradox. Earth twin stays on Earth. Rocket twin flies on a rocket at some relativistic speed. Okay. Earth twin pulls out a telescope and watches rocket twin and views a shortened rocket. Given the differing perceptions in the length of the rocket, what is the speed of the rocket? Right. So this one's a little bit more algebra involved. Okay. Let's do this contraction. So this is going to be, I'll say from Earth twin's point of view, is equal to length rocket from rocket twin's point of view, or you could call it rest length. I could call it like L naught rest length, right? Multiplied by this Lorentz factor, 1 minus b squared on c squared. Okay, right? Now I see 4 variables here. The rest length, the contracted length, the speed of light, and the speed of the ship. Right? And I gave you on this paper 3 of those. Right? So the speed of light is given. Right? I told you what the rest length is, or you could say rocket twins perception light. Like suppose the rocket was 10 meters long. So before it blasts off, both Earth twin and rocket twin break out some meter 6, and they both agree, yeah, it's 10 meters long. Right? Rocket twin flies close to the speed of light. Now, as long as you're along for the ride with rocket twin, you always perceive the ship to be 10 meters long. You keep measuring it, but you say it's always 10 meters. Right? But Earth twin looking through his telescope says something happened. Right? It's shorter than that. Right? So I gave you that value too. It says it's only like 5 meters long or something. Right? So there's enough information there where you can solve for what is the speed of the rocket. Do you guys think you can do the algebra and solve for that? Right. So that one I want to give you guys some independence to work on. So I'll give you guys some class time later. But you guys see the setup how you do solve that in principle, right? Right. Number 3. A particle physicist, maybe over at CERN, possibly, accelerates a particle around a synchrotron. That could be like Large Hadron Collider as a synchrotron, right? Giant loop or speeding up particles around, close to the speed of light. The given mass being steered by the magnets is given, so many grams. What was the rest mass of the particles? So this is mass dilation I was telling you guys about. And particle physicists see this all the time. So number 3, I got the dilated mass is equal to the rest mass divided by the Lorentz factor. 1 minus b squared on c squared. Okay. So the idea is that, let's say put in like 1 gram of hydrogen and then speed it up close to the speed of light. It's going to appear like there's more and more mass. Or actually, yesterday I called this a momentum dilation. So let's just do the mass version of that, right? You need like a stronger magnetic field to keep it in circular orbit, right? Right. So for this one, I gave you the dilated mass steered by the magnets. I gave you the speed of the particles and speed of light. So can you solve for the rest mass? Right. There's only one algebra step for this one. You just cross multiply the Lorentz factor. That's it. All right. You guys can do that too, right? You do that. And so again, I'll leave that to you guys. All right. You guys some independence there. All right. And let's do 2 more questions together here. Number 4, number 6 is what we got today. So, and they're related to each other. All right. Number 4, some amount of mass. Let's convert completely into energy by a nuclear reaction. How many joules of energy? Right. So I gave you some mass. I have 6 kilograms here. Let's suppose that completely converts into energy, maybe with matter, antimatter, or maybe we're talking about a change, right? What if you start off with like 1,000 kilograms of uranium in a nuclear reaction? Now you have 994 kilograms of uranium. That's a difference of 6 kilograms. So maybe you could interpret it that way. So however you want to interpret it, right? How much energy we're talking about. So I'm going to start number 4 as E equals mc squared, right? There's your mass energy equivalence. Well, if I told you the mass in kilograms, then you got that. I told you the speed of light, you got that. Square the speed of light. You put it all together, you get the energy measured in joules. Do you guys think you can do E equals mc squared? Is that right? And then number 6 is actually related to that. Let's check out number 6. It says, you are a resident of a spaceship moving between stars in the galaxy, and each person is going to consume an average of so many kilowatt hours of energy per day, right? Now, my paper says 40 kilowatt hours of energy per day. Where did I get that number from? Right. That's first of all, it's kind of a weird unit for energy. In this class, we usually say some number of joules. I went with kilowatt hours because that's maybe usually how a utility bill, how your bill is number of kilowatt hours, right? Also, I picked numbers that is kind of a median value for living in a developed country, like the States, right? Right. Think about that for a moment. It's like how much energy all of us use every day, and some of it's obvious, and some of it's maybe less obvious, right? So like any food you eat, right? Well, there's energy there. There's a whole agricultural process behind that, right? The growing of food, the transportation, the pumping of the water, right? Every time you turn on the faucet, there's some pumps out there, right? Got the lights in the room, got air conditioning, you guys got laptops and screens, right? Those all take energy, right? How about anytime you buy anything, right? There was a manufacturing process and a transportation process, right? So all that is embedded in some amount of energy, like so many kilowatt hours of energy per day, that are associated with living in a developed country, right? So let's just let's just copy paste that into space and say like, right, suppose you have back to this setup here. The spaceship's fuel storage contains some amount of fuel per person, per resident here. How long before you have to refuel? So here's where all of us have slightly different numbers, probably. Mine says 0.01 kilograms, right? Now, one of the points of this particular question is I want you guys to see, like, what is the context of nuclear energy? Like, how much energy are we really talking about? Okay. So let's convert that to grams. Guys, 0.01 kilograms. How many grams is that? What does kilo mean? Kilo is a factor of 1,000, which is 3 decimal places. So roll 1, 2, 3 decimal places. How many grams? 10. 10, which happens to be your smallest lab weight. You guys know those little boxes of lab weights, right? The smallest one is 10 grams. You could have this in your pocket and not even know because it's so tiny, right? So what if I convert this completely into energy? Maybe, again, it could be like matter, antimatter, or maybe we're talking about some mass change, right? So if this was completely converted into energy by a nuclear reaction, E equals mc squared, which is how you kickstart this, right? And then I use this energy at the rate that all of us are using it just living in a developed country, right? How long would it last you? You guys get that premise, right? So the first step is E equals mc squared to just get some number of joules, right? You guys got that, right? So the second step is I need to convert that into how long is that going to last if I use it at some rate. And I set you guys up a dimensional analysis table. You guys see some railroad tracks here? I have most of the table. I didn't do the whole thing, right? There is, let's throw in one more step. Here, one more step. Can you guys add a little bit to your railroad tracks table? One more step, right? So look at the units. I got joules per resident. Here's joules, kilowatt seconds, kilowatt hours, seconds to hours, cancels, right? The one conversion factor I'm missing is this is going to solve how many days this lasts. And guys, look at the answer choices. All the answer choices are in how many years. Do you guys see that? Right? So what's the last step you need? How do you convert days to years? Yeah, divide by 365. Exactly. There's 365 days in 1 year. Right? That'll complete the table. So you do equals mc squared, say how many joules of energy, and then you use this table to convert to how many years that lasts. Right? Now, regardless of what the exact answer is, I'm looking at my answer choices, right? All my answer choices are in the ballpark of 10,000 years. Here's like, they're somewhere in the ballpark of 10,000 years. Is that? So that's what I want you guys to get out of this. It's like even a tiny amount of mass, if you convert it all into energy and use that energy at pretty good clip, right? This could last you like 10,000 years of energy is what that would be, right? So, right. You guys get that? Right. All right, so let's do this. I want to give you guys most of the rest of the class to work on the puzzles that we've been going over today. And then the last couple minutes of class, I'm going to play a 2-minute proof for E equals MC squared, where that really comes from, right? So go ahead, see if you guys can figure these out, navigate the algebra, help each other out. If you're really stuck, then ask me and I'll help you out too.